project with my colleague Apostolos first, Prasas from UBITECH, and also the colleagues from UP, Kostis and Christos. Well, the UPF is one of the essential functions of 5G for many reasons. It first and foremost separates the control from the user plane, allows high-performance data forwarding. It acts as a policy enforcement point, supports network slicing, local breakouts, and an important thing is also that it offers programmability at the point where you can apply it. And this is what we try to leverage here. So as you may know, legacy UPFs are deployed on commodity hardware nowadays, and this can be a bit restrictive sometimes by means of performance when you want to meet high performance standards like ultra low latency slices or high throughput slices. So the need is basically to find a way to offload traffic for those demanding slices into the hardware and achieve higher performance, but without losing the flexibility that software-based deployments offer. And let's delve into the objectives of the work. Well, we chose to offload the UPF data plane not in any kind of hardware, but rather into the network to exploit high performance and provide a fast equivalent solution to the typical kernel-based UPFs that we have nowadays. The second thing we try to achieve in this work is that we try to provide this functionality via a closed-loop service. So when something happens in the network and you need this kind of high-performance UPF, you can have it on demand. And finally, ensure that these kind of UPFs can coexist with the legacy ones, and yet both be integrated with a real 5G core system, not just emulation or simulation stuff. What challenges we have seen in this effort? Well, first of all, to provide an offloaded UPF into the network, and especially in P4, which is our target, can be really complex. So you have to deal with low-level instructions on the switch level down here. So we had to elevate this up to the end user and provide abstractions. This is why we use DFS as a first abstraction layer to create a UPF service on top of what the switch is doing. And then even higher to do it at the intent level using OpenSlice and try to abstract further. The second thing is that we had to pick the right tools so that we make this realistic for a network operator. So as I said previously, we don't want to just emulate the whole thing. We want to use a real 5G core, and the tools that we pick to simulate things or to make them simpler, let's say, are still realistic. So we use OpenAir interface G-Node B simulator to mimic the behavior of a real 5G G-Node B, which is integrated with a real 5G core. And then as an equivalent of a real Tofino, let's say, switch, which would be the case for a network operator, we use ONF's legacy systems like Stratum and SD Fabric to actually provide an equivalent implementation, which works in both cases. All this is end-to-end integrated with a real 5G system based on OpenAir interface, and it provides equivalence with the real deployments. A bit of background in 5G before we start. So at a high level, the role of UPF is a kind of bridge between the UE side and the data network side. So when the UE wants to access a given data network, it goes through the G-Node B. This opens a GTP tunnel towards the UPF function. And on the other side, the UPF has to decap the traffic and send it towards the data network on the one way. And on the way back, it does the reverse. So it's a kind of a router, basically. So this is overall how a simplified UPF works in 5G. And what is the methodology that we follow in this demonstration? Well, we use, first of all, an end-to-end 5G deployment. We're using OpenAir interface core. This deploys all necessary core functions, including a legacy UPF. And we associate this legacy UPF with one data network, which is the internet in this case. And then we demonstrate the need for another UPF, which is based on P4, and it's offloaded. to introduce, let's say, another data network, number 2, which is a kind of a privileged one with high performance services and the need to have higher performance. And on top, we introduce this closed loop, which basically monitors the whole 5G system. And upon an event, let's say a gold user appears and wants high performance, we instantiate this UPF on demand using OpenSlice and TerraFlow SDN. So briefly, the relation with the SDGs. Well, we have done a lot of work here to integrate the different systems together. First of all, there is cross-SDG relation because we integrated OpenSlice with TFS. We integrate also OpenSlice with Prometheus to be able to close the loop and pull monitoring metrics from the 5G system. And then there's a lot of integration happening in SDN, in TerraFlow SDN with ONF projects and P4, like SD Fabric, Stratum, and so on. So we have done pretty much work in all these areas. Before I start the demo and the whole scenario, let's see a bit of detail about how we implemented this UPF. This is the pipeline of tables for the UPF when the packet traverses the uplink. So we start from left to right. The UE is here with a given IP address and tries to ping the IP address of the data network, which in this case is 10.10.2.2. So the packet has to be encapsulated first between the G-node B and the UPF. It enters the UPF pipeline, which is in this case implemented in P4 via the SD Fabric, and undergoes all these tables in P4, as you see them linked with arrows, before it reaches the egress part towards the data network. I'm not going to go into details. I'm happy to take those details tomorrow in our presentation in the booth. But you see that there are a lot of tables being involved here for filtering the traffic, doing the ingress functionality of the UPF, forwarding, routing, even quality of service, access control. So lots of them. The same thing in a reverse manner happens when the data network replies with towards the UE again. So we have to take the opposite path. The packet enters again the same pipeline, but now there are a bit of differences here because we need to involve the reverse, let's say, functionality to encapsulate now the traffic towards the G-node B and some other details of the pipeline until we reach again the UE. So it's a complex pipeline, and as you understand, we don't expect the user to know how to program all these tables at the P4 level. This is why we use TFS, and this is why we use OpenSlice on top to really abstract all these details. What is the scenario? We have split the scenario in phases, let's say, just to demonstrate in an easy way this whole demo. First, we just deal with the legacy users here and the legacy UPF. So we deploy in one VM the whole 5G core, including a legacy UPF, and also a G-node B, simulated G-node B with a couple of UEs, which are associated with the first data network, the internet. This is how typically you can use Open Air interface today to do everything in one box, let's say in one VM. Next, we demand, let's say, a different class of users to be connected to the same 5G core. We call them slice 2 users here, the green ones on the left. And these are the privileged users that they need to access a different data network, number 2, through a high-performance UPF, which in this case goes through this second VM here, in which we need to deploy the Stratum switch. And this is controlled by TFS, which is sitting in this VM here. How do we actually combine both now? We use a scenario where we integrate the telemetry of the 5G system with OpenSlice. And when this slice 2 user appears, we know that this is the time that OpenSlice needs to provision the UPF on demand, the P4 UPF on demand. And this is what OpenSlice does. It has a service, it pulls monitoring data here, and then actuates when some condition is met by instructing TFS and the switch to actually provision the UPF. The workflow. We start the demo with a clean state. Let's say we showcase how OpenSlice, the state of OpenSlice, the state of TFS, and the various components initially. Then we showcase how we design this service at the OpenSlice level to close the loop. And we order this service to be materialized. And then we have two scenarios. The first is the introduction of the silver class user equipment, which go to the legacy UPF. And then the gold class UE, which needs to go through the P4 UPF. Let's see how those things are combined together now. We started with the first workflow. So initially, we browse the OpenSlice marketplace through the UI, and we showcase that there is a deployed, developed, designed service, which is called P4-offloaded 5G UPF. This is the service we have designed to actually provision this whole thing. Initially, TFS is empty. It's deployed, but it doesn't really run anything yet. And we start by deploying the 5G core dynamically. So all the functions go up, including the legacy UPF. And this legacy UPF is associated with DNN1. At the same time, we also deploy the SD Fabric UPF, which is a control plane, let's say, component add-on in the 5G core, which is connected with this environment here, which has the PFCP agent and the plugin towards TFS. And at the bottom side, we showcase the environment where the UPF, the P4 UPF is going to be hosted. So this is the target environment for the P4 UPF. We deploy Stratum there, but it's also empty at the beginning. So it doesn't run any P4 program, it doesn't have any rules, it's not configured at all. So nothing happens in this UPF. And then we showcase the telemetry of the 5G system, which is important for us here to close the loop. So let's start with this phase of the demo first. So I'm going to play out the demo, the first phase of the demo. So this is the OpenSlice portal. We connect there and we go to the marketplace to see this P4 UPF service, as you see on the right-hand side. We check this out here. We also showcase that TFS is empty at the beginning, doesn't have any topology, any devices, any services, any links. So it's a clean state environment. And now we go into a low-level terminal to start the 5G core. It's a bit too small for you maybe to notice, but it's the time that we do a Docker Compose up to bring up all the functions of the 5G core. These are depicted up here, and on the top we have a watch command which showcases the services that are spawned up in this cluster. We showcase that DNN1 Internet UPF is already up, and also the SD Fabric UPF, which connects the UEs to the intranet, is also available. But this is just the control plane at the moment. There is no UPF in the data plane. Now we go into another console and we start the Stratum switch in the P4 UPF data plane. Again, this is just an empty switch at the moment. It doesn't run any code, nothing. And we also deploy Prometheus so as to be able to close the loop with OpenSlice. So all the components are bringing up at the moment. Here you also see the oh yeah, now at this point I have to stop the demo because we're entering the phase 2. So let's go back to the slides to showcase phase 2 now. All the system components are up. And now we're going to go into phase 2, which is how we have designed the closed loop service in OpenSlice and how we are ordering the service. To do this, we have first of all to connect OpenSlice with the telemetry data that is available through Prometheus. So it's the left-hand side of the diagram. And then once we are able to stream those metrics into the OpenSlice service, we bundle, let's say, this service with another one which actuates and calls TFS on the other side to instantiate the UPF. So once we order this service, all the necessary components bring up OpenSlice establishes bindings with Prometheus to pull the metrics and is ready when the metrics are triggered and the thresholds are triggered to actually call TFS as well. So let's now go to the second phase of the demo. So we are in the order list now of OpenSlice. We order this service and we go here to acknowledge the order and proceed with provisioning of the right services. So we see here several services get active in OpenSlice. And this is the service graph that is created by OpenSlice when trying to implement this closed loop. So you see here one service that calls TFS. This is the actuation service that deploys the UPF. And two other services which are monitoring the Prometheus metrics from the UEs, both for the silver UEs and the gold UEs. So going back now to the characteristics of this service, we see here that we have the two metrics of interest for the gold UEs and the silver UEs. So there's a counter for both. Whenever we connect a UE here, this counter will be updated. And now it's the time to actually bring up something, which is phase 3 for our demo. So we go back to the third phase of the demo now, in which we introduce the silver user equipment that go through the legacy UPF. How this is happening? We instantiate the G-Node B simulator with one UE at a time. So when the UE is deployed, OpenSlice picks up the update. So the metric, the number of silver UEs in OpenSlice becomes 1. Nothing happens at the moment. OpenSlice doesn't trigger anything at this point. And we just test that this UE actually is able to ping the internet. So this is functioning well. So the legacy UPF functions as intended. And we go to the instantiation of a second UE in the same way. Again, the metric in OpenSlice becomes 2 now because there are 2 UEs in the system. And again, the second UE is also able to reach the internet the same way. So let's see how this is happening. We do a Docker compose app command to deploy the G-Node B simulator with the first UE and then the second UE. And we see that these things are coming up on top. And now we're gonna see the interface of this first UE, the IP address and so on, and instantiate a ping command from the UE to Google. This is working fine, so it has connectivity to the internet. And if we refresh here the system, we see that the metric now has become 2. There are 2 UEs connected to the internet, and this is also reflected in OpenSlice. So we go to the last phase now, in which we're going to introduce a gold class UE, which has to go through the UPF function in P4. Again, we instantiate another G-Node B simulator here, which has a UE of a gold class. And now, just to demonstrate you that this is real, we kind of freeze the time. We deliberately delay OpenSlice to pick up this new metric from Prometheus, let's say, to demonstrate to you that when the UE brings up, the UPF is not yet provisioned by OpenSlice. We freeze the time. We delay this decision by OpenSlice to show you that initially the ping doesn't work. So the UE is up. It tries to ping DNN2, but the switch is not yet configured by OpenSlice. It's empty. So when it tries to ping, it fails. Then we kind of unfreeze the time and let OpenSlice pick up the update. The number of gold UEs now becomes 1. This is the trigger for OpenSlice to provision the P4 UPF. It indeed happens via TFS. Now the switch has the right program and the right set of rules to realize the UPF. And when we resume back to the console, we see that the ping now is working. In parallel, we also demonstrate that the legacy UPFs that we had previously started still are able to ping DNN1. So both types of UPFs coexist through the same 5G core. And if we attempt now to tear down the stratum switch, we will see eventually that the ping stops in the UPF side. So let's try to go the last mile now of the demonstration. It's the time that we introduce the gold UE in the system. Now, the same way, we will try to identify the IP address of this UE and attempt to ping the DNN number 2. You see that the ping now is towards 10.10.2.2, and it doesn't work initially. It's the moment that OpenSlice is a bit frozen. So we now go to the Prometheus side to see the metric. We unfreeze the time again. We see now that the metric has become 1 in Prometheus. This is picked up by OpenSlice eventually. And this is the time that OpenSlice now knows that it needs to invoke the TFS API to provision the UPF. So we see number of gold UEs is 1. The service is triggered. And we're going to visit the TFS UI now to see that this is really happening. You see all services are active now in OpenSlice, including the last one about the trigger of TFS. So the order gets completed. And it's the time to go to the TFS UI now. We update, we refresh, and we see suddenly a topology, which in this case includes the P4 switch in the middle. On top, it's the TFS controller and the 5G core, which have established control plane interactions with the UPF. And at the bottom, you see the 5G G node B on the left-hand side and the data network on the right-hand side. This is the set of devices that comprise the topology. This is the P4 switch specifically, which has a quite long list of P4 rules, as you may see. It's all this set of tables that I showed you earlier. They need to be configured with actual rules in P4. So this is what it is depicted here. The links of the topology are also displayed in this tab. And finally, the service, the P4 UPF service, and its configuration is shown here. So TerraFlow did the job, configured the switch already. And now if we get back to the console, we see that the ping has already started. So the gold UE is now able to reach DNN number 2. And this is the time that we will also showcase what is happening in the DNN2 side. So we do a TCP dump in this data network number 2 to showcase that actually it receives packets from the UE. And we now split the terminal in two to demonstrate that the silver UEs, which are still active in the 5G core, are still able to ping the first data network through the legacy UPF. So in other words, we demonstrate that both UPFs coexist at the same time, and they're able to access different kinds of services. Now we stop the stratum switch, so no more forwarding happens in the P4 UPF, and you see that the gold UE now stops receiving ping responses anymore. This is because there's nothing going through the UPF anymore. Stratum is down. So as I said, this is also a booth tomorrow, or the day after actually. There is a demo upstairs regarding this work. The team behind, as I explained previously, this is in context of the Across project, which is now over. And at this point, I'm happy to take any questions you may have.